Okay, here we go. Now, the first speaker of this session is Jaydeep Kumar Basak from IIT Kanpur. So he will be talking about islands for entanglement negativity. Basak, Jaydeep, I will get back to you at 11:55.
Okay,
Please go ahead.
thanks.
Yeah.
Thanks.
Yeah.
Yeah. First, I would like to thank the organizer for giving me this opportunity to speak here. Today, I will be speaking on Island for Entanglement Negativity, which was done with these people. They were Shiv, Vinayak, Himanshu, and Gautam Sengupta. This will be the rough outline of my talk, where I will try to first speak about entanglement and correlation measures in QIT, then a short review of the holographic proposal, and then the main part, which is the island proposal for negativity. I will again try to sketch some of the double holographic scenarios. I will try to show some of our result. And if time permits, I will go to the replicable part. Otherwise, I am going to summarize my talk. So entanglement negativity is a measure of entanglement in mixed state. Let's take a mixed state A, which consists of A1 and A2. In that scenario, Vidal and Warner in 2001, they proposed negativity as a computable measure of entanglement of a bipartite system in a mixed state, which can be written in this specific way. Now, what is this rho AT2? To understand that, we can take EI and EJ are two bases in Hilbert spaces, which corresponds to A1 and A2, these two intervals here. Then partial transpose density matrix can be given in this specific way, where we can see the color coding here that EJ and EL in the left hand side has been interchanged their position in the right hand side. In this same context, Perez-Seradoki PPT criteria is another important criteria, which says that a necessary condition for separability of state is that the eigenvalue should remain positive if we perform this partial transpose operation over one of the subsystems. Here, rho 82 means that we are performing the partial transpose operation on the second interval A2. Now, if I say according to this Perez-Seradoki PPT criteria, we can say that negativity is also a measure of the extent to which the eigenvalues are negative if we perform the partial transpose operation. In a mathematical way, we can write in this specific manner. Another point is that entanglement negativity provides the upper bound on distributable entanglement, which is basically the amount of quantum entanglement that can be extracted from a mixed state if we only use LOCC. In the context of mixed state, reflected entropy is another measure of that. Now, Pratik gave a nice talk on this same topic. So here, what we can say that A and B are two intervals here or two subsystems here, which consists a system which is a mixed state, and we try to purify it canonically by taking A star and B star, which are basically the copy of A and B. In that case, where we have A, B, A star, and B star, we can define a pure state root over rho AB, such that we can get back rho AB if we trace out A star B star from this density matrix here. When we have A B A star B star, we can say that SR is defined as the von Neumann entropy of A star or the von Neumann entropy of B star. Now, if we start from the very beginning that A and B in a pure state, in that case, we can say that reflected entropy is going to be twice of SA or it's going to be twice of SB. The holographic Rayleigh entropy is related to codimension 2 cosmic ray, which is homologous to the subsystem A. A is the subsystem which is sitting at the boundary, and now this cosmic brane has a tension which is proportional to n-1 by n. Now here we see that if we take n going to 1 limit, we can say that the tension is going to vanish, and in that case, we will recover the RT. Now, going to the next topic, which is the holographic reflected entropy. It has a nice dual, which is called entanglement wedge cross section. It can be defined as a codimension 2 surface with minimized area dividing the total wedge of A and B. Now, to understand that, we can look in this figure here, where A and B are two subsystems here. and we have a connected wedge. So now we can also have a disconnected wedge where A and B can be sitting far away. In that case, the situation will be quite different. But here we just take the connected wedge sector, where this blue area is the wedge of A union B, and we try to find the cross section of this blue area, which is the dotted surface here, and we try to again minimize it, and finally we get the entanglement wedge cross section. Now to explain the holographic reflected entropy, we have to take another copy of that, and we take that because we want to accommodate A star and B star as we explained before. And then we just cut out this red area and try to glue these two wedge region along this RT. And what we get is the right hand side scenario. Now here we have A star and B star, and the wedges are glued along this RT here. In this scenario, we try to find out the von Neumann entropy of A star or B star. In both the cases, what we get is this blue circle here. And so it is nothing but twice of the area of EWCS. So we can say that SR is twice the area of EWCS here. Now holographic entanglement negativity has also a nice interpretation here, but it has basically two different proposals. First proposal was proposed in these two papers, where holographic entanglement negativity was proposed as an algebraic sum of brane entropies of order half. Now we take a disjoint interval A and B here, and C is an interval which is sandwiched in between A and B. And in that case, if we consider it as DCFT2, negativity can be expressed in this precise manner. But we see that these terms, S half A union C, these are like Rayleigh entropy of order half. Now we have to take different kind of combination here, A union C or B union C, A union B union C, or C alone, and we can formulate the negativity here. Now when we have the answer for disjoint interval, we can also take C to be very, very small. In that case, what we will get is the adjacent interval result. By taking that, we're going to come here, and also we can write that negativity is half of this, the mutual information of order half. So that is another outcome of this result. Now again, the single interval case is quite tricky, where we have to consider B1 and B2, two auxiliary intervals on both sides of A, and then we take bipartite limit, where we take B1 in and B2 is full AC or A complement. In that bipartite limit, the negativity can be written in this specific manner here. Now all the results coming from these proposals match exactly with the CFT2 result if we consider the central charge to be very large. There is another proposal which says that entanglement negativity is related to the reflected entropy of order half. It was proposed in these two papers. In the first paper, negativity was proposed to be the dual to back reacted EWCS, and also in that same paper, a quantum corrected version was developed, which can be written in this specific manner. Now, in the later paper, a concise version was also proposed, where negativity was written as half of reflected entropy of order half. Now, further in this paper, the sum of the result of this paper was further refined, and that was the outcome of this paper, the third one. Now, before going to the island proposal for entanglement negativity, first I will try to go through the island for entanglement entropy. The key point of this is that fine grain entropy of a region in QFT, which is coupled to a semi-classical gravity, is given by the island formula, which is written in this specific way. Now, this ISA is the island corresponding to the subsystem A, and this term is the effective von Neumann entropy of quantum matter fields present in A union island of A. Now, from a pictorial point of view, we can say that this is in the bath region, or this is the region where only QFT lies, or if we consider only ADS3 CFT or that dimension, we can say that CFT2 is living on this bath, and we have this JT brane, which gives us the semi-classical gravity here. Also, the CFT2 is extended in this region as well. Now, if we try to find out the entanglement entropy of the region A, we have to consider another region which is buried inside this jetty brane, which is ISA, or the island of A. Now, having these two regions, we can now write this island formula, where the first term is giving us the area of the endpoint of islands, and second term is usually giving us the effective volume and entropy. In the same way, we can write the island for reflected entropy, where it was proposed in these two papers. It was written that SR has a sum of two different terms. First term is twice the area of a special surface, which is Q prime. Now, Q prime is the intersection of the boundary of reflected island A and reflected island B. And the second term was the effective reflected entropy of bulk quantum matter fields between these two regions. Now, this Q prime is a special surface here, which is denoted here in this picture in this black dot. We have considered A and B to be two subsystems here in the bath, and then we try to configure the reflected island A and reflected island B here. So we can say that in general, reflected island and entropy islands are not exactly same, but yes, we can say that when we have the entanglement entropy island for A union B, which is this region here, the full region here, we can chop it into two parts. One part we can name it as reflected island A, and another part is reflected island B. This is what is happening here. So we are having the contribution of the first term from this black dot, and the second term is basically the effective reflected entropy. In the same way, we are going to propose island for entanglement negativity. Now, if we go through the first proposal, then we try to define the any generalized island formula for entanglement entropy in this way, where we see that the formula has been raised to an index n. Now, if we follow the first proposal, which says that negativity is related to a special sum of uh, any reflected entropy of order half, we can now express the island formula for negativity as a combination of generalized any entropy of order half. Now, here we consider the two disjoint interval A and B. Of course, C is there, but C is sandwiched in between A and B. And in that scenario, we can write generalized negativity as the half of the special combination of generalized any entropy of order half. Now, when we have this, we can take this answer and we try to extremize over Q double prime surface. And if we get more than one suit, then we will take the minimum answer, and that will be my island corrected formula for negativity. Now, what is this Q double prime surface? Q double prime surface is the intersection of the boundary of negativity island A and negativity island B. Here also, when we have the island for total A union B, entropy island of A union B, we can again chop it into two parts, where we can name one as negativity island A and name another with negativity island B. And in general, we can say that these negativity islands and entropy islands are not exactly the same. Now, having the disjoint case result, we can take C to be very, very small, and we can come to this result where we can have the generalized negativity for two disjoint intervals. Now, for single interval as well, we can again take B1 and B2 to be two auxiliary interval on either side of A, and finally taking this precise bipartite limit, we can have this answer. Now, in all the cases, we have to take the sum and then perform the extremization and minimization over the parameter Q double prime. Now, here we say that whenever we take the sum, all the parameters except Q double prime gets cancelled out. So whatever is remaining, that is only Q double prime here. So we have to extremize and minimize over the single parameter, which is Q double prime. Now, we can also come to the island for negativity using the second proposal, where we have to first define the any generalized reflected entropy. It can be written in the specific manner, where we see that N and M are two indices now. Now we take M going to 1 and N going to half limit to get the generalized any reflected entropy of order half. Now, when we have that, we can write generalized negativity as half of generalized reflected entropy of order half. Now, the When we have these two proposals in hand, we can write a generalized island formula for negativity, which can be look like this one here, where we have a generalized negativity as the sum of two parts. The first term is a back-reacted area of Q double prime surface, and the second part is the effective negativity of bulk quantum matter fields between these two regions. Now, this Q double prime surface is the same as I explained before. It is the intersection of the boundary of corresponding negativity island A and negativity island B. Now, I will try to sketch some of the double holographic scenario for this proposal. First, I will try to explain some double holography for entropy, which is proposed in this paper. But yes, we can have many more names here as well. So key point of this proposal is that the island formula for entropy can be written as the sum of two area terms here. Now the first area term is the same as we have seen in the island formula, but what about the second area term? For that, we have to consider the CFT2, which is lying on this whole region, to be holographic. In that case, we can expect a bulk dual which is lying here, and if we can consider that, then we can write the second term, which was the effective entropy term of interval A union island of A. We can write that in terms of area, which is this one, this blue line. So we can see that the island formula for entropy can be written as the sum of this blue line, the area of this line, and also this special green dot sitting here. Now, in the same way, we can explain a double holography for reflected entropy as it was proposed in these two papers. It is the sum of, again, the two area terms here. The first area term is this special green dot, which is sitting at the intersection of the reflected island A, reflected island B, and also the second area term, which is basically giving us the entanglement wedge cross section in this region. In the same way, we can understand our negativity proposals. For that, we try to consider the double holography expression for generalized Rayleigh entropy of order half. Now, here we say that that entangling surface has the spherical symmetry. Now, when we have the spherical symmetry, we can write the special form where we can write S gen of order half as a proportionality constant times the S generalized entanglement entropy of order 1. Now, in that case, we say that this is the proportionality constant which depends on the dimension and also the geometry of the surface. Now, when we have the expression for generalized Rayleigh entropy of order half, we can again take the combination and we can propose negativity in this form. Now, also according to the second proposal, we can propose double holographic scenario for entanglement negativity, but the SR half, the S generalized half, can be replaced as chi d times SR. If we do that, we will get this precise formula here, and we can write negativity as the curly line. But now we have the liberty to take it here, the back reaction effect here, and we can write that this is the dashed line and the green line, a green dot here, which is the second this term in the bracket, and we just multiply with chi d terms, and we get the answer. Now I will try to show some of our result. We have considered a specific model which was explained in this paper, where a zero temperature black hole was considered in 2D JT gravity with the matter given by CFT2. And we then couple it to a bath living in the half Minkowski space, which has the same CFT2. And then finally, we impose transparent boundary condition for the easy flow of modes. And in that case, if we take a single interval 0 to b in the bath, we can write the generalized entropy in this manner, where phi is the corresponding dilaton fields, and phi naught denotes a constant which contributes to the topological entropy. Now here we consider an interval C1, C2 in the bath, and also we have corresponding island AC1 and AC2. In that case, we try to write generalized Rayleigh entropy of order half, which can be written in this specific manner, where we see that we have multiplied this chi2 terms, which is 3 by 2, we have taken chi2 because we are considering ATS3 CFT2 scenario, and these 3 by 2 terms are only multiplied in the second and third terms, not the first one, because the second and third terms are only the dynamical term here. So they are only going to get the back reaction effect. Now, when we have set the model, we can now consider two disjoint interval. One is from B1 to B2, this one, which can be named as A, and B3 to B4, which is this one, which can also be named as B. And then we try to compute negativity from both the proposals. And what we get is the answer, this one, written here. So both the proposals are giving the same answer. Now, uh, we can change the size of the subsystems here. We can change the subsystem size A, B, or both, and we can have many more phases. Now just take a situation where A and B are small. In that case, if this is the subsystem we consider C, then C is very large. In that case, A, B both has the disconnected wedge. In that case, when we have the disconnected wedge, intermittent wedge cross section is identically 0. So negativity is also 0. And if we just invoke the same condition in the first scenario, we can also get the negativity to be 0. Another condition is that we can have A to be very, very small. In that case, what we have is this EWCS line is going to land here in this black RT. So we can calculate negativity for this kind of situation as well. And also, if we try to invoke the same condition in this scenario, and we try to compute entanglement negativity via the first proposal, we are going to get the same result as the second proposal. So we can say that all the results are matching for all the phases. And we can then go to the adjacent interval case and as well as the single interval case. And there also we see that the exact matching of result from both the sides. Further, we consider another model where an eternal black hole has been considered in 2D JT gravity with matter given by CFT2. Now we couple two rigid half Minkowski space on either side of the gravity region with the same CFT2, and then we impose transparent boundary condition at the interface. In that scenario, as earlier, we take another interval C1, C2 on one side of the bar. Now it has an island AC1 and AC2. In that case, we again write generalized any entropy of order half in the specific form. Here also we see that the proportionality constant chi2, which is 3 by 2 again, is multiplied in the second and third term only, not the first term. Now, in this situation, we can consider two disjoint interval. Now here it is A and B. One is in the left side and there is the right side. And we can have C, which is a very small. We can say that it is some interval which is sandwiched in between A and B. And in that case, we try to use both of the proposals to compute negativity. And what we get from both the proposals is this answer. Now, one crucial point is that here we have to take C to be very, very small. Otherwise, the wedge of A and B will be disconnected one. In that case, we will get 0 negativity. So we can consider different type of phases, and also we can consider negativity for adjacent and single interval case. And what we saw that the result using both the proposal match exactly for all the cases. Now, as I have time, I will go to the replica wormhole scenario where we see, where we first understand, we will start try to understand this construction in this paper, where negativity was proposed as even analytic continuation of Rayleigh index 2n. Now, this 2n replicated boundary manifold is M2n AB, where A, B denotes the fact that A and B pollute cyclically and anticyclically respectively. Now, this Z2n symmetry on the boundary doesn't always extend to the bulk saddle points. Now, we will get the most interesting result when this Z2n symmetry doesn't extend to the bulk saddle points. But when it does, what we get is identically 0 result for negativity. Now, this one is called replica non-symmetric saddle. We have to take to a number of copies, and on each copies of bulk manifold, we consider a cut along three non-overlapping codimension 1 homology hypersurface. This is sigma A, sigma B, and sigma AB bar with this specific condition. Now this gamma X denotes a codimension 2 hypersurface here. Now when we have this scenario, we try to glue along this sigma A surface the odd number of copies of bulk manifold cyclically and even copies to themselves. We can see it from this figure. These odd copies 1, 3, 5 we can do cyclically for A and B with themselves. Now the same way for sigma B, we try to glue the even number of copies of bulk manifold anticyclically and odd copies to themselves. And for sigma AB bar, all
Jaydeep, you have about 5
hello.
minutes left.
Okay,
You have
thanks,
about
thanks.
5 minutes left. Yeah.
Okay, thanks. And for sigma AB bar, all the copies we glue pairwise, starting with the first one, finishing with the last two. Now, if we glue in this specific manner, the replica symmetry group Z2n breaks into a subgroup Zn. Now, taking the Zn quotient manifold, we can have the asymptotic boundary M2a, b, which is in case the same as M2ab, because when we have two copies, you can't differentiate between cyclically and anticyclically. Now, the quotient manifold has a conical defect at gamma A1 and gamma B2. And we have the backreacting cosmic branes, which is homologous to the subsystem A and B with this specific deficit angle. And then we go ahead, we can go ahead with the calculation, and we get the negativity as a half of mutual information of order half. Now, if we just try to accommodate island for this replica non-symmetric saddle, we consider a quantum field theory coupled to a gravity on a hybrid manifold M, where M fixed is non-gravitating and M bulk contains dynamical gravity. Now, this quantum field theory is extended throughout the M, but gravity is bounded in M bulk only. Now, we use the same procedure as explained before, and what we get is this specific answer, where generalized negativity can be written as half of generalized mutual information of order half. Now, if we consider two adjacent interval results, the above result match exactly. But what about the disjoint case result? So in that case, we take A and B, two separated interval, which is disjoint interval, and C is there as well as it's another disjoint interval, which is sandwiched in between A and B. It makes the full system A union B union C compact and also makes it a pure state. In that case, if we try to compute generalized negativity, we can have this specific formula. Also, for a single interval A with two auxiliary interval B1 and B2, we can have the generalized negativity as the specific manner when we consider this bipartite limit. Now, these three are the formula which we have used in the first proposal. So we can say that the first proposal has a proof in this manner uh, using the replica wormhole scenario. Now I will try to summarize my talk that we propose two alternative construction for island contribution to the entanglement negativity. The first proposal involves specific algebraic sum of generalized any entropy of order half. The second proposal involves generalized any entropy of order half, and we applied our island proposal to compute negativity for various cases, and what we saw that the results match exactly for all the configurations. We also tried to sketch a possible double holographic scenario for our island proposal, and also in the end we obtained a proof of our result using replica wormhole technique. So in this context, I would like to say that uh, the matching of this result, one from the algebraic sum, another from the generalized Renyi reflected entropy order half, the matches only up to a constant. Recently, there has been a paper where we see that this match is only up to a constant, but the functional form match exactly. Okay, so that's what I have to say. Thank you.
Okay. Let us thank Jaydeep for a nice talk. If there are any questions, comments, you may please raise your hand. any questions, comments? Okay, if there are no questions or comments, let's thank Jaydeep again for a nice talk. And I would like to see if Akrajyoti is already here.
Yes, yes.
Jaydeep, you may stop your screen.
Hi, Jaydeep. I have one question, very basic question.
Yeah. Please go ahead.
Yeah. Yes.
Why do we need entanglement negativity? I mean, this is one moment entropy is not enough for some reason.
Yes, so for the mixed state, we need entanglement negativity, because in mixed state, what entanglement entropy gives us is not exactly the entanglement what we need. As example, I can tell you that for finite temperature CFT, if we consider single interval there, and you try to compute entanglement entropy, what you will get is the entanglement entropy and also the thermal contribution there. So that's what we don't need. We need only the entanglement we only need the quantum entanglement from a mixed state. In that case, you have to consider entanglement negativity. That's the way out.
Okay, thank you.
Yeah, thanks.
Hello. Hello.
Yeah, Akrajyoti.
Yeah.
Kindly share your screen and
Yes,
go to
yes.
full screen mode.